Hello everyone, let's continue. And in this video, we are going to discuss two very basic concepts related to binary search, which are quite important, and they are a part of a lot of harder problems as well, right? So the concepts that we are going to discuss here are lower bound and upper bound. Now, many programming languages have this inbuilt methods. For example, in C++, you have this lower bound, upper bound. In Python, you have something like bisect, left bisect, right? But here we will write our own lower bound and upper bound. So let's get started. And first of all, we will try to understand what is the lower bound, right? And then we will basically implement it. So lower bound, very first index where value is greater than or equal to x. For example, lower bound of the function where you will pass some target, let's say x, and it will return you the very first index in the sorted array where value is greater than or equal to x. Obviously, both of these things applies to only sorted arrays. So if you have some kind of this array 1, 2, 4, 4 and 6, and if I ask you lower bound of 4, then you can return index 2 because 2 is the very first index where value is greater than or equal to x. And if we are asked to get the lower bound of 5, then we need to return 2, 3, 4 because 4 is the very first index where the value which is 6 which is greater than or equal to 5, right? So how to now solve this? Let's take some random array. Let's say this is the array, right? And here we are expected to find the lower bound of 6, maybe like 6, and we need to return 3. Now in this thing, let's say x is 6. Now if you observe carefully, one thing is the array is sorted, so for sure we can apply binary search because our search space will be monotonic. But we can actually divide this array into two halves depending upon our target. One half has values less than x and other half having values greater than or equal to x. Can't we do that? And in this half, we are expected to return the very first index. So as discussed in the previous video, we can model every binary search problem to the problem related to finding the last zero or the first one. So in this array again, we can see we can clearly divide this array into two halves. So this half can be visualized as segment comprising of zeros, and this half can be visualized as segment comprising of ones, right? And in this half, you are expected to find the very first one because if I find the very first one, which would be at index 3, synonymous to this 7, so you can just simply return index 3 as your answer, right? Now, obviously, you have you don't have the privilege to convert this array to this array because this is just for visualization. We are expected to find both of the results to both of this function in log of n time, right? If you convert this array to this array, then obviously you will do n operations here itself, so that will defeat the purpose of the whole algorithm. This is just for our visualization. If we are in this segment where the value is greater than or equal to x, you can visualize it as 1, right? And then you can just accordingly update the pointers over here. But I won't do that for this array because we have did this previously. I will do this for this array, right? So you can do this for this as well, but just for the sake of understanding, I am doing it for the original array, right? So we were asked a lower bound of 6, which was the very first index where value is greater than or equal to 6. So this is going to be 7, right? So now, if I am at, if let's say I am my mid is somewhere over here, which means I am at some point in this interval, right? Then definitely going to the right part is useless, because since I'm interested in finding the very first index, so I'll search it in the left half. Also, I need to update my answer, which we have discussed previously, because it might be the case that your mid is somewhere over here, and this is the very last time you are searching in, like you have a value which is greater than or equal to your asked value, which is 6, and then you will be moving to the left part for searching. So you have to update your answer over here, right? And if you are in this part where like the value is strictly less than whatever we are asked, then for sure, like going to the left part is useless, because all the values will be smaller. Only we need to consider searching in the right half, right? So definitely that's how you can do this. And now let's try to implement this thing, right? So let's try to create a function, private int lower bound, and we have a target int. So it returns the very first index where value is greater than or equal to target. Now, what if all the values are smaller than target? So, for example, let's say you have something like 2, 3, 5, and your target is, let's say, 10. Then definitely you don't have any indexes where value is greater than or equal to target. So, in this case, you will return n, because maybe like you can insert 10 over here, or however you want to visualize this thing. So, we can just initialize our result by n. Why? Let's see. So, the length of the array is a dot length, and initially the search space will be for the entire array, right? Standard binary search. Now if you are, let's say, at some index which has a value greater than or equal to target, right, then you are in this segment, and definitely this is one of the potential answers where you are standing, because it might be the case that this is the last time you are seeing a value greater than or equal to x, right? So after this you need to search it in the left half, right? So result is mid. Go in the left half by decrementing the high pointer and setting it to mid minus 1. Else you need to go to the right half, and you can just simply return res over here. Now why I have initialized result to n, this is important, because let's say if this condition never gets hit, which means no value is greater than or equal to target, so we will ideally end up at this case, and in this case you can insert 10 at the end, right? So now let's try to take some array, random array. We will take this array only 2, 3, 5, 7, 10, 10. Now we are, if let's say I print lower bound of a comma 6, right, then I should get 3. Let's try to run this. This works. Now if I try lower bound of 5, then I should get 2, because this is the very first index where value is greater than or equal to 5. I got 2, right? So this works correctly. Now let's move to binary, not binary search, upper bound, right? So what is upper bound? Upper bound is the very first index where value is strictly greater than x. So upper bound is a function which will take x as parameter, right? And it will return the very first index where value is greater than, strictly greater than x. Here we had equal to sign as well. So if I take this thing 2, 3, 5, 7, 10, right? So if I ask you what is the upper bound of 5, then we are expected to return index 3 because this is the very first time when value is greater than x. And if we asked upper bound of 4, then we need to return 5 over here because 5 is the second index is the very first index where value is greater than 4. Now how to do this? Very simple. According to this array, right? If we are asked let's say if we are asked x is equal to 4, then we need to figure out the very first index where value is greater than 4. So definitely we can divide our subspace into these two halves. And similarly, if we are in this half, then we need to search it in the left because there is no point going in the right because the values will be greater and we are interested in finding the very first value, right? And if we are in this half, then again, like going to the left is useless because we want the value greater than x, so we will go to the right. Now this was when, so you divided this thing into less than x, or I should say less than or equal to x. Now why less than equal to x? Let's say you had x as 5, then you would have divided its subspace into 2, 3, 5, 7, 10. This was the array. Then you would have divided the subspace like this because we want the index where value is strictly greater than x. So from this point onwards, all the values are valid, right? So you can again visualize this as 0, this thing, right? And yeah, that's pretty much it. And here you can just simply figure out the very first one. So if your mid is somewhere over here, then going to the right is useless because every value will be strictly greater than, like the every index will be strictly greater than x. We need to go to the left part because we are interested in finding the very first index. This could be one potential answer, as I've already discussed it many a times, because this could be the very last time when you can see a value greater than x, right? So now let's try to implement this thing. And if a of mid is greater than target, then you are in this thing. You are in the segment comprising of 1, so you need to search it in the left half. Otherwise, you need to go into to the right half. Right? So just by changing one sign, I can just convert this lower bound to upper bound, right? Now let's try to run this thing, and for the upper bound of 7, I should get index 4. I got 4. And let's say if I place 4 over here, then I should get 2 because 5 is the very first time. Yeah. So this also works, and we have discussed both of these lower bound and upper bound concepts, and these are quite like useful concepts. And we will see, like in many binary search problems, in like many harder problems, these two are quite frequently used, right? Now we will do one problem, and this problem is actually based on a similar concept, right? So here we are given a sorted array of distinct integers and some target value. We need to return the index if target is found. If not, return the index where it would be if it were inserted. So for example, if you have this array, target is 5. If target is present, return that index, which would be 2, right? And here target is not present, so you need to return 1 because we need to return that index where it would be if it were inserted. So if you had this array, let's say 1 3 5 6, and target is, let's say, 2, and if target is 2, then definitely if you insert it at index 1, so your array will remain sorted. So you can just displace this element one by one to the right? So isn't this problem exactly similar to finding the lower bound? Because if I find the lower bound in this case, then what was the lower bound? the very first index where value is greater than or equal to x. So 3 is the very first index, not 3, value 3, which would eventually lead it to 1. And in cases where like the value is present, for example, if you were searching, let's say for 5, right, then definitely you need to return 2. And what does lower bound states? It says first index where value is greater than or equal to x. So eventually you will land up at 5 only. So this is just a simple lower bound, right? So let's implement this real quick. Right? Int low is equal to, now although like the upper bound would work in cases when the target is not present, but it won't work in the cases when the target is present, because in this problem if you do a upper bound of 5, then you will get index 3, because that is the value that is strictly greater than 5, right? So we need to do a lower bound, right? So you can just simply do a binary search over this, and you can just figure out the mid. If a of mid, nums of mid is greater than or equal to target, then we need to search it in the left half, else we need to go to the right half. That's it. And we can just simply return result similar to how we implemented the lower bound function, right? Let's try to run this thing and works on samples. Yeah, this works correctly. So if we discuss the time and space, then time is again a simple binary search. This check is again a constant time. So log of n, and we aren't using some kind of space as well, just some variables, right? So yeah, that's pretty much it. Thanks for watching.